So now it's a real pleasure for me to introduce tonight's distinguished speaker, Csaki from Cornell University. I'll run through his bio, although it's in your handout here. He obtained his bachelor's degree at Eötvös University in Hungary. He obtained his PhD at MIT under the supervision of Lisa Randall in 1997. He was a Miller Fellow at UC Berkeley and an Oppenheimer Fellow at Los Alamos National Laboratory before joining the Cornell faculty in 2002. Csaba is a particle theorist whose research focuses on possible new phenomena beyond the standard model of particle physics. He explores various extensions of the Higgs mechanism giving rise to all elementary particle masses, supersymmetric theories and models with extra dimension. He would like to understand if there are new particles or interactions within the reach of the current Large Hadron Collider or future colliders, and how one may most efficiently discover them. Csaba was a Department of Energy Outstanding Junior Investigator. He received the Research Prize from the Humboldt Foundation in Germany, and he was elected Fellow of the American Physical Society. He is currently on the board of the Aspen Center for Physics. And let me just say, personally, I've known Csaba for 20 years, and he, to me, is one of the most influential and creative theorists trying to understand, ultimately, the dynamics that is responsible for the masses of elementary particles. So it's with great pleasure I introduce Professor Csaki.
Thank you very much, Howie, for the introduction. And would just like to reiterate again how amazing this place is, the Aspen Center for Physics. I have been coming here ever since 1998. I think it's probably my 20th year here, so also a pretty round number. And also how great the town of Aspen actually is. It's really amazing that we can fill this lecture every week, so thank you so much for coming and being a loyal fan of ours. So the plan for today is for me to first to talk a little bit about what is particle physics, what is it that we already know for sure about particle physics, and how do we know it, and then tell you about our future plans, what is happening right now, and what we are hoping would be happening in the not too far distant future, maybe such that we still even live to see it. So probably many of you know that we are aware of four basic forces in nature, and they are the electromagnetic force, and everybody is aware of that. It gives rise to electricity, waves, radio waves, light. Then there's a second one, it's called the weak force. That's a little bit less obvious, but it's the one that is giving rise to radioactivity, for example. Yes, the nuclear beta decays are an example of the weak force. Then there are the strong interactions, and those are even somewhat less obvious, less commonly thought of, though they are very important for us. They are the origin of energy from the sun, and they bind the protons together inside the nuclei, so they are really important. Okay, and then there's the gravitational force, the gravitational interaction. Of course, everybody is aware of this, especially here in Aspen when we try to fight it every day when we hike the Ute Trail or some other even higher mountains. Now it turns out that the gravitational force is actually much weaker than these other three forces. And on first sight, again, being in Aspen, fighting it every day, it may look counterintuitive, but if you think about it, that a small magnet can actually balance the effect of the entire Earth, then maybe it's not so shocking for you to realize that actually, the gravitational interactions are much weaker than these other three. So it turns out that for particle physics, the kind of experiments that we are investigating is really most of the time these first three forces that are the relevant ones. And gravity, every now and then we'll mention it a little bit, but many times in particle physics we can just ignore the gravitational interactions. So how to think about these different forces that I have listed for you? Well, the modern picture of how we are thinking about these particle physics interactions can be nicely summarized by this little cartoon here, where we are imagining that there are two skaters that are skating parallel to each other, but for some weird reason, one of these skaters is, holding a, heavy bowling ball, okay? And then, for some reason, at some moment, the skater decides to pass the bowling ball over to the other skater, okay? And the other one is going to catch it. What will happen is that both of these skaters, due to the fact that they have passed this bowling ball to each other, they're going to be deflected from their original parallel path. Yes? So if I look at this from far away and don't even notice that there was a bowling ball that was exchanged, it looks like there was a repulsive force that was acting between these two skaters. And that's actually a pretty precise analogy of how we are thinking about these fundamental interactions nowadays. We are drawing these little cartoon diagrams. They are called the Feynman diagrams. And what we say is that all of these forces that I listed actually have a mediating particle. So think of it as like this bowling ball. And so each of these forces have a mediator, a force mediator. And that's how the matter particles are going to be interacting with each other. So this is how we are thinking about, for example, electromagnetic repulsion when two electrons are close to each other. Okay, so again, these little cartoons are actually taken seriously by physicists, and they are called the Feynman diagrams. And this is how we are actually describing, all the particle physics interactions that we are aware of. And again, so these were invented by Feynman, and this is how we are thinking, for example, about the modern version of electrodynamics. The theory of light and Maxwell's theory of electricity and magnetism is called quantum electrodynamics, and it's basically just explaining, how likely it is that, one of these photons is going to be emitted, how likely it is that it's going to be captured by the other particle, how to describe these forces. Okay, so, and I put a little picture here just to emphasize that, yes, Feynman was at Cornell when he did this important stuff, just so that nobody forgets that. And it was only a short period. He was there only for about 4 years after the Manhattan Project before he moved on to Caltech. Now, so this is something that we sort of knew, explain how the modern theory of electrodynamics works. By the 1930s, there was a version, and then Feynman came up with his really nice intuitive version in the 40s and 50s. And then the big question was, what about these other interactions, the weak and the strong interactions? Now, the big surprise that came sort of around the 1970s is that actually the weak and the strong interactions are not that much different fundamentally from the electromagnetic interactions. There is a force carrier for the weak interactions also, very similar as the photon, the quantum of light being the force carrier of electromagnetism. There is a force carrier for the weak interaction, and physicists, they are not that creative, so they said weak interaction, okay, it's the W particle, that's the force carrier for the weak interaction, so it's easy to remember, yes. And again, fundamentally, the structure of the theory is very similar. There's one big difference between the weak and the electromagnetic interactions, namely that this W particle, this force carrier, actually turns out to be massive. Because it's massive, it's actually not a stable particle, but it doesn't want to travel for a very long distance, but it itself is going to decay. Okay, the photon is a massless particle, it's the quantum of light, so it travels with the speed of light, doesn't have any mass. But this object, the force carrier for the weak interactions, is very heavy, it's a sluggish, doesn't want to go up a mountain, wants to decay to two other particles. Okay, and that's why it is actually weak, because it doesn't have a long range. It's not weak because there is a fundamental difference between the probability of emitting these particles. It turns out that's very, very similar. The main difference is that this W particle is actually heavy and is unstable, so it will only live for a very short period of time. Okay? And then it turned out that in order for you to formulate a complete theory of the weak interactions, you can't just get away with a single force carrier. Okay? So that's another big difference between the weak and the strong interactions, that there is actually another force carrier, which we call the Z boson, and the main difference between these two particles is that the W is electrically charged, and the Z boson is actually electrically neutral. So it's somewhat similar to the photon, which is also electrically neutral, yes, but it's a very heavy version of it. So these are the force carriers of the weak interactions, the W and the Z. Otherwise, the theory is really fundamentally, described in the same little cartoons that you use for electromagnetism. Okay, so this was, these were the three theorists who have really predicted, how to describe the theory of this W and the Z, the probability of them being emitted and decaying. So this is Glashow, Salam, and Weinberg, and turns out these two were actually Cornell undergraduates. Just if there's a team here, yes. And so they were predicting these W and Z bosons, and so these were the first events where these W and Z bosons were actually created in a particle physics experiment at CERN. And then here's the picture when they were toasting for the Nobel Prize of the experimentalists who have actually discovered these particles. Okay, so that's the story of the weak interactions. Again, the interaction that is responsible for radioactivity, beta decay, and all those phenomena. But then there's one more that I told you is relevant for particle physics, which is the strong interaction. And that one seemed in the 1950s completely different from the electromagnetic and the weak interactions. And the big surprise that came after a lot of experimental and theoretical work in the 1970s is that actually fundamentally the strong interactions are not that different in terms of how we are describing them. There is a description in terms of the same kind of little Feynman diagrams, little cartoons. The big difference is that the fundamental part, so initially I told you that the strong interactions are the ones that are binding the proton and the neutron into nuclei, and that's how we were thinking initially about the strong interactions. The big surprise was that the fundamental version of the strong interaction is actually acting on some more fundamental constituents than the proton and the neutron. There are the so-called quarks, which are the constituents, the more elementary particles than the proton and the neutron, that the proton and the neutron are not elementary, but are made out of quarks. But once you look at the interaction of the quarks, it is the same kind of theory, that there is a force carrier for the strong interactions. They are called the gluon. Yes? And otherwise, you can really think of it still in terms of these Feynman diagrams, just like the previous theories. So the main difference is that the probability of emitting this mediator is very, very high. So for the case of electrodynamics, it's a really good approximation that you just take one photon and exchange that, and that's going to be, approximately good description of a process. Here, the probability of emitting a gluon is very large, so you should also take into account emitting 2, 3. So that's why these strong interactions are going to be really strong, because the probability of emitting this gluon is going to be very large, and that will actually bind these quarks together into bound states. So you will never see these bound states, you will never see the quarks as elementary particles. The quarks are the basic strongly interacting particles, but you never see them as free particles. They are actually confined inside the so-called hadrons. Okay, so they are glued together by this exchange of these force carriers of the gluons. Okay, so this was actually a really big step forward, yes, and it was Gell-Mann who actually just passed away a few months ago, and his funeral was actually here in Aspen. He was one of the very early Aspenites, and he played a very important role in the history of the center. So he was the one who realized that probably there's some more fundamental object inside the protons, these quarks, and he was able to sort of classify the many hundreds of strongly interacting particles that were discovered in the 1950s and make sense of it, put them into little multiplets, and also make predictions about other ones that haven't been discovered at the time. Okay, so that is one of the important stories about the strong interactions. And there's one more important distinction between the strong and the weak and the electromagnetic interactions, and that's a pretty counterintuitive fact, and we call that the asymptotic freedom of the strong interactions. So again, the strong interactions, the basic, property of them is that they are strong. Yes, that's what their name is. They are strong interactions. Now it turns out that that's actually not always true. If you start colliding these particles at higher and higher energies, these interactions are actually starting to get weaker and weaker and weaker. Okay, so the strong interactions are actually not always strong. If you go to extreme high energies, then they become weak, and that's what this weird name, this asymptotic freedom, is actually referring to, that these quarks that I told you, well, we never see them as free particles, yes, but if you smash them together at very, very high energies, they will still behave as if they were free particles. So asymptotically, at super high energies, they are going to be behaving like free particles. Okay, so that was one of the really important ingredients that then allowed the theorists here, Gross, Politzer, and Wilczek, to write down the precise theory that can be used for calculations and for predictions of the results of experiments. So that was sort of the last sort of very important missing ingredient that allowed us to establish what the right description of the strong interactions is. So these are basically the underlying facts of this beautiful model that is now called the standard model of particle physics. Yes, and again, the main feature is that there are matter fields. Yes, so we call them the fermions. So those happen to have spin 1/2, but if you don't know what, doesn't matter. So those are the matter fields, the matter particles. Yes, and they come in two versions. The leptons, those are matter particles that are not strongly interacting. And quarks are the matter particles that feel the strong interaction. And then there are these other set of particles which are the force mediators. Okay? So that's basically what the standard model of particle physics is. Okay? And it turned out that we have this theory, the standard model of particle physics, and of course physicists like to test them. And before this LHC, which is one of the experiments I will be talking about, turned on, a lot of the predictions of the standard model have been verified to a very large precision. And it doesn't matter exactly what these quantities mean. They were measured at the predecessor experiment at CERN, which was called LAP. There were about 20 different quantities that theorists were able to predict to like 0.1% precision, roughly. And the experiment was able to measure it at CERN. Yes, and basically find agreement with every single aspect of the theory. There was one important aspect of the standard model that has been unchecked before the LHC turned on, and that is the story of the Higgs boson and the bigger story of what we call electroweak symmetry breaking. So I told you that we have this theory that is called the standard model, and there are rules there, how to write down the different interactions, how to make predictions for different processes. And it turned out that when you write down the standard model, there's one important aspect of it, that every particle, when you write down the theory to begin with, has to be massless. You cannot add a mass to these particles. Okay, the basic principles of the standard model forbid writing a mass. And for the photon, that's great because the photon is massless. We know it's light. It's traveling with the speed of light. But I just told you that, for example, the main property of the W and the Z boson is that they are very, very heavy. They want to move very slowly, sluggishly. So what's going on here? And it turns out all the matter fields also didn't get any mass in the standard model. So the physicists decided that, well, there's got to be something else that is missing. Yes? There's one more sector, one more important ingredient that I haven't explained to you that we have to add to the standard model, namely that there's another particle, another field, which we call the Higgs field or the Higgs sector, that actually will break some of the symmetries of the standard model. Okay, so let me try to explain quickly, what this Higgs mechanism is. Okay, so what we are saying is that, well, the entire space is actually going to be filled by some sort of an invisible fluid. We call that the Higgs condensate. Okay, so the entire space is really filled with this sort of fluid or condensate. Yes? And it's the interaction of the particles with this fluid or condensate that is actually appear them to be slowing down, that will appear them to be massless. Okay, so once you take into account the interaction of these particles with this background fluid that is filling all of space, yes, they will appear to be gaining mass. Okay, so here's a little cartoon, yes. So there's all of space here, and the photon is a massless particle, so it just doesn't feel this fluid that is around. The fluid is around, but the photon just doesn't feel it, so it just happily moves on. The electron has a little bit of a mass, so every now and then it bumps into this fluid and slows down a little bit. Yes. Then there are the quarks. The up quark is a little heavier, so it bumps into this fluid a little more often. And the top quark is the heaviest known elementary particle, so that bumps in a lot into this fluid, so it slows down a lot. So, that sounds really nice, but some of you may may say that this sounds really weird. It sounds like a theory that physicists have long ago abandoned. Yes, sounds like a theory of ether. Yes. Back, in the 19th century, people were wondering about electromagnetic waves. Yes, people knew that every wave needs a medium in which it is propagating. Yes, we know that, water waves, well, they need water to propagate. Sound waves, they need air to propagate. Yes, and then there are electromagnetic waves. So people were wondering, so what's the medium for electromagnetic waves? Yes, he said, I don't know, but it's probably something, so I call it ether. Yes, and that was a really important, question. Yes? So people were looking for this particular ether, and they found that such a thing does not exist. Yes? And that was the basic thing about relativity. That was the foundation that let Einstein formulate the theory of relativity. Okay, so now you may be wondering, so if that ether was excluded, then how come now I'm saying the same thing again? Yes? How come that one is not excluded? Well, it turns out that there is one version of this ether theory which is very specific, that does not break relativity, that is not that is conforming Einstein's theory of relativity. Namely, if this ether looks exactly the same from every observer's point of view. Yes, it doesn't matter how fast you move, that ether looks the same. Okay? So that requires that this fluid has a special property, that it is what the physicists call it a scalar field. The scalar means really that no matter what, how fast you move, it doesn't change. Okay? That's why the Higgs field has to be very different from any other field that we have observed in nature. All the other fields that we know about are not scalars. They do change for an observer that is moving. Yes? And this Higgs field, in order for you to be able to have this whole mechanism where you just say that it's filling all of space, this fluid, as it has to be an elementary scalar. So it really has to be a different kind of particle than we have observed before. Okay? So now there's a little bit of more analogy about the Higgs field. Yes. So the analogy that people usually say is that, oh, this is like you are trying to move a ping pong ball in honey, yes, and then it's actually, it will appear like, because of the honey, yes, it appears like it is going to be heavy. Now it turns out that it's somewhat of an analogy, but not a very precise one, yes, because the damping force that you are usually seeing when you're moving an object inside the fluid is usually either proportional to the velocity or the velocity squared of the object that you're moving inside the fluid. Yes? So you can see that that's actually not quite the kind of phenomenon that means that the particle actually picked up a mass, because if the velocity is 0, there wouldn't be any force. Turns out that the right kind of analogy would be to have a damping force that is actually proportional not to the velocity, yes, but to the acceleration of the particle. And so that's exactly the right analogy. So you can think of the Higgs force as being, just a very special kind of damping force. If you're trying to move the object inside this Higgs fluid, there will be a force that is proportional to the acceleration of the object. Okay, so if there's no acceleration, there is no force. And that's exactly the right kind of analogy for that. All right, very good. So the other important thing is that if this fluid is really existing, then you can also look at the perturbations of this fluid itself. Okay, and that in physics usually corresponds to an actual elementary particle. Okay, so the prediction of this theory was that, if this is the right mechanism for generating mass to particles, then you can move around here, that you can look at small perturbations of this background of this fluid itself, and that should be a particle, and that particle should be interacting with all the other elementary particles that we know about. So that particle is what is called the Higgs boson. Okay, so one of the big goals for the LHC experiment at CERN has been to actually look for this Higgs boson. So this is an experiment that they started designing in the 1980s, and then it was approved in the 1990s, and then construction started in the early 2000s. And it's in Geneva, Switzerland. It has a 17-mile circumference. It's a big particle accelerator that is smashing together protons. Okay, so it's a really amazing experiment. When I saw it, you wouldn't actually believe that it really works. So many people are working on it. Just number of scientists is of the order of 6,000, but it doesn't include all the engineers and the staff member, etc., from all over the world. And here is a little cartoon of what the experiments are. So there's this accelerator, this circular ring where you're smashing together the protons, and there are two important multi-purpose experiments. They are called ATLAS and CMS, and those are the ones that are trying to look for any kind of phenomena that is going to be happening when you're smashing these particles together. And there are two other sort of more specialized experiments. Okay, so I was lucky enough to visit both of these two experiments before they turned on. One of them is called CMS, and the other one is called ATLAS. And if you look at the LHC website, the facts about this accelerator are really mind-boggling. Just the number of magnets, how cold these magnets have to be. It's colder than outer space. How much energy is concentrated in those beams that are actually colliding. Yes, it's like an aircraft carrier moving at 20 kilometers per hour. The vacuum that has to be there in the beam pipe in order for these collisions to not be disturbed by any dust, and the amount of collisions, the accuracy of the timing that is needed, the accuracy of measuring the tracks of the particles that are coming out, as it's 1/50th of the diameter of a human hair. So it's really mind-boggling. Okay, so it started up in September of 2008, and everybody was really happy at the beginning. But then, unfortunately, there was sort of an explosion. There were some of these magnets were not properly connected, and that was, a pretty big event. Many of the magnets had to actually be replaced. You can see, there's a lot of force that is happening here when these superconducting magnets are suddenly heated up. Okay, so there was a lot of damage, but it really amazingly, given how big the damage was, it took CERN only 1 year to repair it. And after 1 year, they restarted the whole experiment, and since then, it has been running very flawlessly and amazingly well. So these were the pictures from the first collisions in 2010. And then, this luminosity is sort of a word that is telling you, how bright the beam is, meaning, how many protons are inside the beam, because the more protons that are inside, then you generate, the more likely it is that you are going to see something interesting in the collisions. So they were able to increase this so-called luminosity, the brightness of the beam, by many factors. So this is from 2010. That was the first year when they had, sort of sizable number of events. Then 2011, much more, and then 2012 was sort of the key year when they were able to make the discovery for the Higgs boson. So this was the amount of data that they have collected by the time that the Higgs boson was actually discovered. And these are, again, these little stick diagrams, these Feynman diagrams that are telling you how the Higgs boson was actually discovered at the LHC. So a proton, I told you, is a bound state of more fundamental particles. So it contains two kinds of particles, gluons and quarks. So when you think about protons being smashed together at the LHC, you can think of as gluons being smashed together or quarks being smashed together. Now it turns out that the gluons are actually massless. So those are some of those particles that don't directly feel the Higgs field, yes? Because I told you that the massless particles, they don't bump into this Higgs, so they don't directly interact. So it turns out that they have to sort of, have a more indirect way of actually producing this Higgs boson. Okay? And then, once you produce it, the Higgs is a very unstable particle, and it will very quickly decay. So when you say that you actually observe the Higgs boson, you are not directly observing the Higgs boson. You observe its decay products. And then, how it decays turns out to be very sensitive to the mass of the Higgs boson. And this is in the units of GeV. And just to give you a hint, so 1 GeV is about the mass of the proton. So it's a pretty heavy object. And here we are talking about 100 times or 125 times the mass of the proton. So it's a very, very heavy particle. So it doesn't want to live for a long time. It decays very quickly. Yes? And how it decays depends very much on the mass of the particle. So this line here is at the actual final mass of the Higgs boson that turned out to be 125 GeV. But if it was heavier, then the decays would have been proceeding completely differently. And the reason why is it so hard to actually find the Higgs boson, and why did it take the LHC 2 years, and why was it not discovered at earlier experiments? Well, it turns out that this number here is telling you what is the probability of producing anything in a collision from protons. Yeah, so this is called sigma total. Doesn't matter. We call it cross-section, but it's basically the probability of producing something in the collision. And you can see this is the probability of producing certain kind of final state particles. Yes? So this is the total cross-section. And if you look here, this is actually a logarithmic scale. So this is, every time I go down here, you are losing 2 orders of magnitude. Yes? So this is the total probability of producing something. Yes? And where is the Higgs? Yes? The probability of producing the Higgs is here. It's 10 orders of magnitude less than producing anything. Yes? So what happens is that you smash these protons together. Yes? There will be something coming out, but most of the time it's totally uninteresting stuff. Only 1 out of 10 billion times in a collision are you going to produce a Higgs boson. So you are stuck with all that data, yes, and you have to fish out the Higgs boson 1 out of 10 billion times. It's even worse than that, because it turns out that the decays of the Higgs are such that many of the actual final states that the Higgs likes to decay to cannot be easily distinguished from the totally uninteresting 10 billion events. So you have to rely on some of the very rare decays of the Higgs boson itself. And so it's actually the mode where the Higgs was discovered was decays to photons. So this is the gamma-gamma mode. You see that's already only like 1 in a few hundred of the decays is going to be to that, or the decays to 2 Z bosons. Okay, so it's really, that's why it's so hard. You have all that data, and you have to fish out, the very few interesting ones out of it. Okay. But they did it. It's pretty amazing. And so this was the big announcement on the 4th of July. So people say the Higgs boson was born on the 4th of July of 2012. So this was the big excitement of the announcement. And you see, this is just the people outside the hall who couldn't get into the actual announcement. And then this is Peter Higgs, and this is Francois Englert. So those were the 2 physicists who first predicted the existence of the Higgs boson back in the 1960s. Okay, and then the way, again, the Higgs boson was actually discovered was by looking at this very rare decay mode of the Higgs, which is to 2 photons. Yes. And what the experimental colleagues did is they were looking for any event that contained 2 photons, yes, and they were trying to see, did it actually come from some other particle? And this little bump is telling you that this little axis here over many other uninteresting events, those are the ones that are sort of suggesting that there was an extra particle that was decaying to photons. So this little axis here over the background, this bump, is what is telling you that there was a new particle there. Okay, and then the similar thing about the decay to another mode, which is the 2 Z bosons. Okay, so that was the big discovery of 2012, and the Nobel Prize was given already basically immediately, as quickly as possible. That's very rare, yes, because 2013 Nobel Prize was the earliest one that could have been given to the discovery for the Higgs boson too. So this is Peter Higgs and Francois Engler. All right, so we discovered the Higgs. That's really great. We have the standard model. Now what? Yes. So where is particle physics going? Well, prior to the results from the LHC, we were actually hoping for other very spectacular discoveries, and some of you may have heard. I will talk a little bit more about these very spectacular kind of things that could have been seen at the LHC. One of them is called supersymmetry. In that case, for every particle we have observed so far, there would have been a new partner. Extra dimensions of space. The Higgs boson maybe is a composite, and each of those would have predicted the existence of other new particles besides the Higgs boson. Okay, so far, unfortunately, we haven't seen any of these, and these models are starting to be severely constrained by the non-discovery of the LHC. So I guess the question that we should ask is, were the physicists lying about these theories? And should we call now the LHC a failure or a success? And that's really important because you may have seen in the media, some people started to say that, oh, the LHC actually, was a failure because it failed to deliver, the exciting discoveries that scientists have promised. So this was an op-ed in the New York Times. And so it's really important to understand, what it means for an experiment to be a success, and when is it a failure, yes? So when should we, try to repeat those? So first of all, a really important experiment usually is exploring a new frontier of science, yes? Examples are, for example, the moon landing, yes? That was exploring a new frontier, yes, the moon, or the Mars rovers. Medical experiments can explore new treatments. The Space Telescope looks, further into space than anybody else did before. In particle physics, the new frontier usually means that you go to as high energies as possible, to energies that have never been seen before. Okay, so the LHC is a prime example. It is in exploring energies almost 10 times the previously achieved energies at Fermilab. Okay? So we are clearly in unexplored territory, yes? And the important thing that these frontier experiments are trying to do is establish what the laws of physics are at those energies, yes? Do the same laws of physics still apply that did apply at lower energies, or do you have to change the laws of physics when you go to these higher energies, yes? Such change of law of physics sometimes does happen. When you go from macroscopic scales down to microscopic scales, down to atomic scales, you have to switch from classical mechanics to quantum mechanics, yes? And this is the kind of thing that we are trying to explore, yes? And sometimes it turns out you have to switch, and sometimes it turns out you don't have to switch, okay? So when we do one of these frontier experiments, yes, by definition, we cannot guarantee the discovery of a particular outcome. Yes? If we did, then that wouldn't be a new discovery. We would already know that that thing is there. Yes? By definition, you can never guarantee a particular discovery. Yes? So I would say that a frontier experiment is successful if it actually thoroughly explores what the laws of nature are at that frontier. Yes? If it discovers anything new, it's a spectacular success. But if it does explore it thoroughly, then it already is a success. Yes, it's a failure if it misses something or if the experiment doesn't work. But it's a success if it can do what it set out to do. Just to give you an illustration, yes, I mean, you could have said the same thing about, the moon landing, yes. I mean, we didn't know what's on the moon, yes. Many people were hoping there will be new life forms on the moon, and that was one of the things that, Apollo was supposed to explore. So should we say after the Apollo landing, oh, it's a failure, it didn't find any new life on moon, so let's stop all space exploration, yes. So, yes. Okay, so another question. So when is an experiment a success? So the predecessor of the LHC was called LAP. Yes, so it was in the same tunnel as the LHC. Yes, and it didn't discover any new particle. Yet, if you ask particle physicists which experiment they think was one of the best they have ever remembered, it's very likely this LAP experiment is going to come up. It is the one that has shown us all this big table of, the standard model is the correct theory, to very large precision, and every particle experimentalist thinks that this was a gigantic success, even though no discoveries. We were still looking for the Higgs boson, we were looking for the top quark. None of those were discovered in this experiment, yet it was a very big success. Now, let me give you another interesting example. So this was, I call it an unlucky near miss. There was a really nice experiment in Italy next to Rome that had an electron-positron collider, and they decided to build it at 3 GeV. Okay, now the experiment was done really well. It was working, wonderfully, except this 3 GeV choice turned out to be extremely unlucky because one of the biggest discoveries in particle physics happened to be at 3.1 GeV. Okay, and this experiment was running since 1969, so it had a 5-year lead. Yes, but because they decided to build it at 3 GeV, they couldn't discover the so-called J-psi particle. And once, the J-psi discovery was announced, they pushed and pushed and pushed the machine, and a few weeks later, they were actually able to get to 3.1 GeV and confirm it. But it was a really unlucky missed opportunity, but I still wouldn't say that it was a failure. When you design an experiment, you have to decide, some parameters, and you didn't know where it is going to be. And now, real failure. Now, this was unfortunately a real failure. Yes, this was called the superconducting super collider, and that's a very sad story, because this was supposed to be an experiment that is 3 times more powerful than the LHC is now. Yes, and it was supposed to be built in the 1990s. And not only was it supposed to be built, but a quarter of the tunnel was already finished. $2 billion were already spent when it was canceled. And unfortunately, we have struggled ever since to regain leadership in particle physics and in high energy physics. Now, let me say a few words of what the situation prior to the LHC was about electroweak symmetry breaking and the Higgs boson. So actually, prior to the LHC, we were in a particularly interesting situation that we don't always have, is that even though I couldn't guarantee you the discovery of any particular new thing, I could guarantee that something will be discovered at the LHC. And the reason for that was that there was one particular process in the standard model that without the Higgs boson would actually just break down. The whole theory would give you nonsensical predictions. Okay, so this was the scattering of W bosons. Of course, the simplest possibility was that, well, there is also a Higgs boson. It's missing from your description. If you add it, that will fix this problem. But there were other possibilities. For example, I had a wonderful theory, which was called the Higgsless model, and it predicted other particles that would have fixed the standard model. And so we didn't know before the LHC, that we for sure are going to be discovering the Higgs boson. We knew we will discover something that will cure the theory, but what exactly it was, we didn't know. Okay. Now, besides this so-called no-lose theorem that is related to the scattering, there was another really nice argument which is called the hierarchy problem. Yes? And that's the one that is allowing you to make the predictions about these other beautiful theories, supersymmetry and extra dimensions. This hierarchy problem is basically telling you that quantum corrections are pushing the mass of the Higgs boson to very, very high values. Okay, so I have a really nice analogy because this looks a bit abstract, but I have a really nice analogy here, yes, which is that actually, the reason why this is happening is that the vacuum that we are in is not an empty space. Yes, well, I already told you there's the Higgs fluid there, but even without the Higgs fluid, the vacuum is always populated with particle-antiparticle pairs that are popping in and out of the vacuum. So the analogy of this hierarchy problem is to say that, well, let me imagine that I have a heat bath that has very, very energetic particles. And now I'm going to shoot one particle into this heat bath that has an energy that is much lower than the temperature of this heat bath. Yes? And this particle is allowed to interact with this heat bath. Yes? Now, imagine that you fish this particle out somehow after a while on the other side, yes, after it interacted with these very violently moving particles. What do you expect the energy of this particle to be when it comes out? Well, because it interacted with all these violently moving other particles, you expect its energy to be pushed up to the temperature of the heat bath. Yes? Now, if you fish it out and it's still just the same very low energy, yes, then you say, well, there must have been something happening here. Yes? Either it doesn't really interact with this heat bath, yes, or there's something special happening that is going to protect you from having the energy pushed up to these very large values. Okay, so this is, again, the hierarchy problem. And so the most plausible solutions for that would be that actually, there are some new particles that are not too far from the mass of the Higgs boson that actually somehow will shield the Higgs from getting these very large corrections. Okay? And the most prominent proposal that does this is indeed this theory that is called supersymmetry, which is saying that, well, for every standard model particle, there would be a so-called superpartner. Okay? So for the electron, there would be a super electron or scalar electron. For the quark, there would be a version of that. And that was the theory of supersymmetry. Another really popular idea that was done by my former supervisor, Lisa Randall and Raman Sundram and many others, is that maybe there are extra space-time dimensions. And that could have had similar kind of effect that would shield the Higgs from getting these large corrections. Okay? Now, again, the question is, if we believe this, where is everybody? So far, there is unfortunately no hint for these new particles beyond the Higgs. This was just a new plot that came out last week about searches for supersymmetry. And again, it has been pushed out to higher and higher values, and it's excluding bigger and bigger regions of these theories. So then the question is, okay, so the experimentalists, they are honest, they did what they should, yes, so it's certainly a success. Did we, the theorists, lie? What, are the theories a failure or what? We promised all these amazing new worlds. Well, I would say, the job of the theorists is really to explore what are the possibilities that can be seen at the next experiment, yes, and hopefully also explaining some of the puzzles, that we are dealing with. And of course, we cannot, promise that that's what the experiment is going to see. Models getting tested and excluded by experiments is the normal progression of science. Yes? And it's not a wasted effort to propose a model that is going to be tested and then excluded. Yes? That's how we are moving forward. Yes? We have to be telling the experimentalists what to look for, yes, in order for them to be able to make the discovery, especially since there's all this stuff that they have to fish out, the very rare, interesting events. Yes? So actually, I really would argue that, having a model that is excluded, that's not a failure. Yes? Having a model that is so uninteresting that nobody looks for it, yes, that's a failure. Yes? Or having a model that is already excluded by data at the time when you propose it, or it's completely inconsistent, that's a failure. Yes? But proposing a model that the experimentalists look for and then exclude, that's the normal progression of science. Okay, so I think that's really important to understand. Yes, and again, the most interesting of these theories is supersymmetry, and we had many reasons to believe that this is something really interesting. It's not like theorists made this up and then try to everybody believe it, but there were very good reasons why we thought that this is the most likely one, because first of all it explained the hierarchy, it was shielding the Higgs from large corrections, yes, but it also naturally explained dark matter. So I'm not going to talk a lot about it because that was last week's topic by Josh Ruderman. It predicted the unification of all forces, predicted many observable new particles at the LHC, and string theory also is not consistent without supersymmetry. Okay, so that is why it was the most favored theory for a long time. Unfortunately, no evidence for it so far. Now, does it mean it's not there, or we are in this unlucky situation where, like with this 3.1 GeV, we don't really know. But the current situation is somewhat unprecedented in the history of science, because we really don't have any direct hints of where to look for new physics. I find it really hard to believe that we are living exactly in the moment of the history of science where we have learned everything and there's nothing more to be learned. Yes? Is it possible? It's possible. Yes. Maybe it's the standard model and nothing else. But I find it very hard to believe that this program that was started by the Greeks and has been going on for centuries, and exactly when I live, that's when it ends. But maybe it's possible. Now, I should also remind you that there were several times before when we already thought that this is the end of science, yes, around the turn of the 19th to 20th century. And then, of course, just a few decades later, quantum mechanics came, and of course, there were many revolutions, yes. But there's still some reasons why we think that there's got to be something beyond the standard model. I told you about the hierarchy. We didn't discover anything yet, so it's getting worse and worse. Dark matter, Josh Ruderman told you about, doesn't fit into the standard model. It looks like it is calling for a new particle beyond the standard model. Now, there are a few other things that people didn't mention. It's really puzzling to understand why the electric charges that we observe in nature are all integer multiples of a basic unit. It doesn't have to be like that, yet it is like that. It's very hard to believe that there is no fundamental reason for that. And if you work really, really hard, the standard model actually does get inconsistent, except at super, super high energies. We will never be able to test them, but at least theoretically we know that there's some energy range where it becomes inconsistent. And maybe gravity has to be quantized too. Of course, these are all indirect and theoretical motivations. There's no real direct experimental evidence, so no direct hint for a scale. So in that sense, it is unprecedented. So what should we do? Well, we just discovered the Higgs boson. It's a completely different particle than anything else. We really have to go and study it in great detail. That's a must. Yes, that's the first thing that we absolutely have to do. The LHC is doing the first steps already. It is looking for the detailed properties of the Higgs boson, and until now, it seems to be all agreeing with the standard model. But there are, the uncertainties are still large enough that a lot of interesting physics can hide there. Okay, and it doesn't quite matter, but in these Higgs couplings, a lot of really interesting new physics can be hiding. So it's really important to try to pin down the properties of the Higgs boson very precisely. So the immediate future for particle physics will be more of the LHC. There will be a lot more data that the LHC is going to bring us. Right now, we are in the middle of this long shutdown, and you can see that after that, they will increase the energy just a little bit, and eventually they will give us more than 10 times, 15 times more data than what we have now. So the best case scenario is we are going to have a discovery from there. Okay. Now, how about after the LHC? Well, the general scientific consensus seems to be, at least to me, interpreting it from not being part of the experimentalists, that probably the best way forward would be to first build a new machine that would study the properties of the Higgs in great detail, Yes, and that would be another electron-positron collider, similar to the predecessor of the LHC, just at higher energies. And the possible locations for this would be either at CERN or in China. And then in the same tunnel, put an even more powerful hadron collider like the LHC and increase the energy level by almost another factor of 10 and see if we have missed anything. Okay, so these are the cartoons for these proposed future colliders. So this would be one possibility at CERN. So you see this is the LHC ring, and this would be an even bigger ring. Yes. You can see that this would be the actual geographic location of that collider. So that's what the CERN is contemplating. Or China is also contemplating building a similar new circular machine. One possible location would be around the place where the Great Wall is actually hitting the sea. So these would be possible options for that. Okay. Another possibility that is being discussed is what is called the International Linear Collider. So that's a different kind of machine. And the upside of that is that it's ready to be built, can do some interesting physics, but it's more limited than what the circular collider could do. The downside is when you build a linear machine, in order to upgrade it to higher energies, it's not enough to put in, bigger magnets or something. You have to keep increasing and increasing and increasing. So it doesn't seem like the most useful possibility, but maybe that's what will happen. Okay. And also the other downside is you cannot use it for a very high energy hadron machine. Okay, so Japan is thinking about building this linear collider, and they have proposals for that. Okay, how about the cost of this? Well, each of this would be of order of $10 billion for the first phase. Sometimes people say $5 billion plus building the tunnel, and this would be over a period of 10 years of construction. Okay, so the earliest any of these new machines could be around is 2030, and the second phase would be more like 2050. So it's very expensive. Now, question is it so expensive that we can afford it or cannot afford it? I put up a few comparisons, okay? And I'm not putting it because I think we shouldn't have national defense or I think we shouldn't have any of these other things. It's just to show you that big projects cost money of this order. Yes, so, a football stadium costs almost that much. Of course, it's completely private money. I think, I like football, so I'm not arguing against it. I'm just saying that, it sounds like a very big amount of money, but this is roughly, nowadays the unit of what big projects cost, and also big scientific projects. Yes, you see the annual NASA budget is $21 billion. And one of the biggest projects costs about the same. Okay, of course, one thing that you may have noticed from my listing of the possible future project is there's one country absent from the list. Yes, that's unfortunately us. Unfortunately, after the cancellation of the SSC, it became very difficult to host a large project in the US, and it doesn't seem to be really realistic anymore that the US is taking a leadership in building one of these very high energy colliders. Of course, that doesn't mean the US is not doing important contributions. It is a very important contributor to the LHC, and hopefully, if any of these other machines are being built, hopefully the US would still participate, but it doesn't seem realistic anymore that it's going to be done right here. Okay, so then the last thing is, so why should we do it? I think we should be honest. The most important reason is that we just want to explore those energy regions. Yes, we want to explore a frontier of energy that we have never seen before. We want to see, are there new particles there, are there new interactions there or not? The concrete goal would be, explore the properties of the Higgs and also the Z boson, and then eventually understand, is that hierarchy really truly there? What does it mean? Or were we just unlucky with the LHC? And if we go another decade in energies, maybe we'll discover something. Of course, there are other possible, arguments for it. Accelerator and magnetic technology is very important. Yes, but I think for scientists, the main reason is we just want to see, is there anything there? Yes. Of course, there could be always unexpected spin-offs. We cannot guarantee that. All right. So just to summarize quickly, we have an amazing framework for particle physics. It's called the Standard Model. It's almost too amazing. It works so well that we don't really have good hints right now of where to go beyond. The last missing piece, the Higgs boson, was discovered in 2012. The LHC so far has been a resounding success, and it's going to deliver 30 times more data in the next decade. So we are still holding out hope that there could be a discovery there. However, so far there is no direct experimental hint for physics beyond the Standard Model, but some indirect arguments are still making us hope for that. There are several possible colliders that are planned. They are all outside the US, and we expect decisions about these within the next 5 years, and it's at least 15 years until we would see, in the best case scenario, any of those new colliders. All right, thank you very much.
We have some time for questions. Go ahead.
The element called Higgs boson is all-encompassing, therefore the analogy to ether,
Yes.
meaning it's everywhere.
Right.
And yet it was a hit-and-miss situation. Hit-and-miss, collide-and-miss situation for so long. Is it now consistent? Can you consistently create that particle
Right.
in the
That's
accelerator?
what the LHC is doing. So it has created it consistently, and what we are hoping is that this next collider that I'm talking about would be a factory of these Higgs bosons, because right now we are producing some, but not a very large number. Yeah, so we want a bigger statistic so that we can study its properties much better. So all of these new colliders initially would start out with a factory of just produce millions of those Higgs bosons.
No question as to how to it's a deterioration process. The particle itself is.
So the particle itself is an unstable particle, yes. So it decays. So you never see the Higgs boson directly. Yes. What you see is the decay products, and then from that you have to interpolate backwards, yes, and say that, well, there was this particle created, yes. So that's.
Because it seemed like so miraculous that one, and it was worded as one was found.
No, it was not one. Yes, so sorry. Let me go back. Yes, so there were many found. Yes, so there was a little bit of. I showed you on that picture. There was this little bit of excess. Yes, and that meant, there were actually still. I think in the initial discovery, there were probably tens of Higgs bosons that created that excess here. Okay, so that was of the order of tens of, and by now there's a lot more. And now you can see it in many different decay modes also. Initially, at the discovery, there were 2 different decay modes that they found it, that were the easiest one to fish out, and by now you see it in many more different decay modes. So it's not a question anymore that there's a particle there, what its mass is, that it looks more or less like the Standard Model Higgs. But of course, we want to see, is it exactly like the Standard Model Higgs? Or, in this 20% slop that I was telling you, maybe there's some other new physics hiding, yes? That's what we want to really discover and explore. You're welcome.
Can you say a little more about that little bump that you're showing us there?
Yes.
You mentioned, I think, during the talk that it was a correlation of 2 particles.
Right, exactly. So what you are looking here is actually 2 photons, yes? And then you have to combine particular properties of those 2 photons, which are called the invariant mass. Okay, so that would be a quantity that you measure all the components of the momenta of the photon, and from that you can create a quantity that would be peaking for if it was the decay of the Higgs boson. That invariant mass would always be at the mass of the Higgs boson. For if the photons came from some other process, they would be just randomly distributed here.
A little more detail. If you're coming in on the z-axis with a particle, how wide a field would you expect to see these 2 particles over? I mean, at 45
So they can be at any, they can be at any angle, yes. But then you make a particular combination of the momenta that you are measuring for the photon, yes. And that particular combination, if it came from a Higgs, would always be at the mass of the Higgs. If it came from somewhere else, it could be anywhere else. So that's why there's a little bit of a bump here, okay? Because you know, all the processes that involve the Higgs, they will always be here. And there are other processes that also produce 2 photons, yes? And that's what gives you, you know, all these other backgrounds, yes? So you're looking for a little bit of a bump. That's the particle physics, you know, discovery, yes.
Is there a theoretical reason for the particular mass of the Higgs boson being?
That's a really good question. That's the $10 billion question, yes? So we don't understand, you know, first of all, why it is light, yes? As I mentioned to you, there's this hierarchy problem, yes? Which we think, you know, if we take an arbitrary, you know, just a random theory, the Higgs boson would not want to stay where it is, okay? So we are taking some special theories where you know, first of all, you know, it stays where it is, and ideally where we can also calculate and predict what the mass of the Higgs boson is. Okay, so those supersymmetric theories or extra-dimensional theories, some of them actually have a prediction for the, you know, not maybe, you know, as maybe sometimes as function of other parameters, but at least you can calculate it. Yes. In the standard model, it's just a random parameter. You know, you know, no prediction at all, not even calculable.
Do you have a good reason why it might be then?
Why it might be 125? Well, we thought so. Yes, we thought when we thought about supersymmetry, we thought it must be in the roughly in that region. But you know, now we are, you know, in this.
Basically, you have to take this as a datum.
It's a data, yes, exactly, and then you know you have to make sure that your models now predict that amount, yes, or it's at least consistent with that mass for the Higgs. Yes, ideally you would want it to be predicted to be. That would be, you know, the best. Will we ever have a theory like that? Well, we are not sure.
Go ahead.
Is the Higgs necessarily unique in the standard model, or could there be
Many
other
Higgses.
particles that would have the
There
same-
could be, there are like supersymmetry would have predicted several Higgses.
It would.
It would, yes. So the LHC is searching for additional Higgs bosons, yes. So definitely, yes. So that would be, you know, and that's one of the things that is actually hard to see, you know, with the, you know, if it's a heavier version. So we are not completely sure that, you know, there isn't any yet. So that, you know, they may still discover new Higgs bosons. That's one of the big important challenges that is left for the next 15 years of the LHC.
Go ahead.
What determines how far underground you have to go in order to set up these experiments?
Just make sure that, you know, there is no radiation coming out off-site. Yes.
How far down is CERN?
How far down, do you
About
remember?
100 meters.
100 meters. Yeah. Yes.
How would the next round of post-LHC be financed?
That's a good question. So if it's done at CERN, so CERN has a fixed budget of, I think, about €1 billion per year. So every member state of CERN is supposed to contribute a fraction of its GDP to CERN. So CERN thinks that out of their annual budget, if somehow, you know, they can get the new tunnel, they could be able to build it. But it takes a long time because, you know, they don't have all that money at once. They can't get like, you know, 5 billion at once. They have to wait. So that's if it's at CERN, yes. And hopefully the US would contribute some amount, yes. Right now, you know, they are contributing some fraction to the LHC. And if it's in China, yes, well, there it's just probably a decision of the, you know, Politburo or the Central Committee. Are we going to do it or not? Yes, is it, you know, I mean, so they certainly are able to do it. They have enough money, but there it's, you know, it's a decision by the politicians, and I don't understand, you know, how that decision mechanism works. But certainly for them would be very interesting, because if they did this, they would certainly become the leaders of a field which involves a lot of technology. So it would really attract, you know, foreign scientists, not because, you know, they pay them, but because the science is interesting. So that would be a very attractive project probably for them. Where is he?
Name it after him.
We would take it for sure. We would be very happy to call it whoever builds it.
Well, he's got it theoretically.
We would be very happy. Do you know his phone number?
All right, no other questions, let's